Okay, before we start, first thing is like anyhow what these are about. So all those things we need to know. So they're like means where DP is used. So basically there are three types of knapsack. One is 01 knapsack. So one is 01 knapsack, which is there. Other one is unbounded, and the third one which is there, which we have already done, that is fractional knapsack. So basically, here fractional we had used in greedy because the most optimized solution which we get for the fractional that we get via greedy. So that's why the best possible way to solve the fractional knapsack is greedy. And then comes the part for the 01 knapsack and unbounded knapsack. So the optimized version of doing these is via DP. Optimize also and even getting the right answer basically. Optimize anyhow it is a different thing, but before that the right answer which we get, that is via this DP solution. So now what 01 knapsack and unbounded knapsack are. So 01, as the name says, it's like either you need to choose it or you don't need to choose it. And unbounded is the one which don't have any boundary. It is just like going it's like infinite supply sort of scenario, that you have something with infinite supply. So that is where unbounded comes into picture. But like more precisely, if we go ahead first about 01. So here in the 01, it's like because it's like either you want to choose or not to choose. First thing is this, and second thing is that there is limited supply. Now comes the part limited supply of what and what exactly the thing is. So here, like you are given some weights. Say you are because anyhow the standard thing which we use is for the weights only. Maybe it will be weights or maybe it's about quantity of like number of items which are there. That could be also possible. Means these are some terms which they use, like number of items also they can use. All these things are there. And there will be something, a bigger container which is there, like some container, and in this, and it also have some weight, say W, the uh, capacity of this container, and some smaller weights which are there, some big one, some small one, like that, and you exactly need to put into the same. And how you need to put that, you attain the maximum capacity, either maximum capacity or near about to maximum capacity, that should be the scenario. But it's like you need to attain that maximum capacity, that so that you have like anyhow anyone will like to have that maximum capacity to earn more profit. So in context to that, so anyhow if the weight all weights are not same, so there could be possibility that some are smaller weights, some are much bigger weights, some are much more bigger weights, like that could be possible. But how you need to actually like even if you use bigger weights also, but there will be some spaces where you can actually have the smaller weights also. So in that context only, you need to optimize in such a manner that whatever maximum possible weights which are there, those you can put into this and you can have the maximum capacity possible. Because there could be possibility that these bigger weights are like, say these bigger weights are like about 6, and then smaller weights are like about 10, and if you fill all the 6 and these smaller weights are in such a manner that these can't even fit inside the spaces which are there. So in that context you need to basically, that is a way of visualizing it. But also other thing is like the way pragmatically or by weighing or like that. So it will be like that you need to check that it is not exceeding the maximum weight. Say it has the maximum weight of say 50, anyhow it will become a lot of big number in context to this example. Like say if we are having some more smaller weights 15, then it will be 25, then around 31, and say some we have much more bigger weights which are around say 20. like that, which are there. But anyhow, we need to do in such a manner that we reach near about 50 or maybe exactly 50, that much weight we gain, so that this is completely filled up. And that also with maximum number of items which are possible. That should be the scenario. So that will be the thing for the 01 knapsack. But here the thing will be that if this is there are six weight of type something, then there are only six. You don't have like you can exceed more than six to fill up the capacity. There won't be that scenario. There's like fixed scenario that if six is there, then you need to use six only. This is for the 01 knapsack where limited supply will be there, and you need to maximize the number of item possible to to fulfill that much amount of uh, basically that much capacity which is there. And now in the unbounded knapsack, only difference will be that there could be possibility that even if 6 is available, you can use more than 6 because there is infinite supply of any particular item which is there. There is just infinite supply of that. So that's why you can even exceed for choosing a particular type of thing. Like for 6 weight, say you are having um, here if we take as product ID, there are some X ID. Again, stones are there. So here also weight is 6, fine. Then there is some X items, and here you can use infinite number of times and put whatever W weight will be there. Say it is around 8, that much only. So here infinite and say that weight is also 1. So like 8 into 1 you can put into the same to fill that particular capacity. Say if you have some Y ID item, this also you have infinite supply and the weight is say 2 weight. Here we have taken weight as 6. Say some Z is there, again it also has infinite supply. So either you can put 8 into 1, that is this one, 8 items, which will be maximum number of items, or you can put basically, or you can put like 2 multiply by 4. So only 4 items you can put. So maximum item you can put these which are there. But anyhow, it will like completely depend upon the question that what exactly they want us to do. Like they want like all type of items to be there in the maximum capacity, or a single item is fine, or they want to ask about that what all combinations are possible. So anything could be there. So that will be as per the question. But the base idea for the 01 knapsack and the unbounded knapsack is this only. In the 01 knapsack, we have limited supply of the weights which are required to be put in the bigger container. And there also it is the same thing that we need to maximize the number of items to be put inside that capacity which is there, and that capacity shouldn't be exceeded, because if it exceeds then anyhow that is just violating the condition. Because it's like in real world also, if we don't have that much capacity, then we can't fill into the same. Anyhow it will then either get rupture or something like that will happen. And in the unbounded knapsack, it's about infinite supply of small items which are there. So we need to optimize that which items we can use at the maximum capacity, means maximum capacity, basically maximum number, so that in a bigger container we have basically maximum number of items under that limited weight which is there in the weight of that container. So that is the only difference about limited supply and infinite supply. Else things will be almost similar, and accordingly even the code will change because of this limited supply infinite supply thing. Else things are anyhow somewhat similar only for both. So I hope you are clear. Okay, fine. And yeah, first I'll show you the template part, then we'll go ahead with the questions which are there. So for the 01 knapsack, first we'll go ahead with the 01 knapsack only. First we'll practice that and then we'll go for unbounded knapsack. So for the 01 knapsack, so the problem is about 01 knapsack is that weight I means smaller weights are given. That is weight of item I, something like that will be there. Then value of I, that is value of the item or item code. So there are like two things. One would be the product ID of that, and the other thing will be the weight of that item. So now we need to see that what question says, that if question says that this is the maximum capacity, that this is the maximum weight we are having for a particular container, and we want that maximum number of items need to be put inside that container which shouldn't exceed that maximum weight. So in that context anyhow we will be checking this weight I for that item, and this value I basically refers to the product ID which is there. That is, this product ID we can use only once because we have only limited supply or how much number they have given. But anyhow, in the 01 knapsack, they will be just given with that this is the item and this is the weight, then this is the item, this is the weight. Like that only means each item will be one time only given to us in 01 knapsack. That is the most of the scenario which is there. So accordingly, we need to like check that how much means which all weight we can put into that container so that we can get maximum number of items being stored in that container. So that all things we will be doing. And then this W is the knapsack capacity. That's the bigger container which is there. So that's W is here. So each item can be taken once or not taken. So basically at most once we can take any item. That's why it's like either you need to choose this or you don't need to choose. That is how the problem statement is always like for a knapsack. It's a inclusive exclusive question. That is either you need to include or you need to exclude that particular item so that you can attain the maximum number of item being stored in that container. So that is the thing. Now, okay, before even we go ahead with code, yeah, anyhow, it is inclusion, exclusion that I had told that how those things are like and how even the recursion tree will be there. That you guys already know. So yeah, we can then go ahead with the code also. Now, for the recursion part, because it's about inclusion or exclusion of a particular item, so how the code will be? It's like that every time we need to take a particular weight or we not to take a particular weight. So here it's like because we are given with this weight I is there, value I is there, and W is there. So basically, we are given with a weight array, value array, and W particular variable will be there. That this is the maximum capacity. These three things are there. So that is what we have taken as anyhow. These are the inputs. That this is the value of that item, and this is the weight of that item, the maximum capacity of that container, and the index for checking that we are at what index, because anyhow these two arrays which will be there that will be of the same size because they are like mapped, that this is the weight and this is its id, then this is the weight, then this is its id, like that. So now for this, the base case, anyhow we know because we are taking this index. So anyhow, yeah, Stuti.
Ma'am, are we supposed to arrange this in descending order based on values?
No, we are not required because here we will be,
Straight away, we just go on iterating the array, is it?
yeah, because we need
Okay.
to figure like what all possibilities are there, that all thing we will be doing. Like if we go ahead with the descending or ascending, so the example which I gave, the visual aspect which was there, if we in the descending also, if we choose all the items, then only smaller will fit in the holes. Maybe there could be some other medium capacity items which could have already been fitted into same and would have maximized the number of item. So that's why ordering them won't matter. So here with the recursion we will be try to find like what all possibilities are there, and out of them which give us the maximum number of items. So that is what we will be doing. So here anyhow base case will be if index equals to 0. So if we are basically starting from the last index, because this index here we are starting from index equals to n, and n equals to weight dot size. So these two things are there. So here if we are starting from the end, even if we don't know that what is the sorting order, ascending or descending of the weights, we are just starting from the end. That is, so when we are starting from the end, so base case will directly turn out to be index equals to 0. That is, we have reached like other end of that array. So if that is the case, we will be checking that if weight of 0 is less than equals to the total weight, then we will be returning value of 0. That is the product ID of that particular weight. Else we will be returning 0. That we don't have any product ID for the same. So now this is the main thing about the question that either we are taking or not taking. When we are not taking, so in that scenario, we will just subtract from that index, because anyhow we need to skip that. So for skipping that, we need to skip its index also. So that's why we are subtracting it. That yeah, we have already basically we have already gone through that index. So that's why we are doing -1. Then because we are skipping it, so that's why nothing got changed in the total capacity. The total capacity will remain same because we are not putting anything into that total capacity because we are skipping this. So that's why this is that not take part. Now about the take part. At the starting initializing with 0, fine. But then we need to have a check, because we can take a particular weight at that point only if our total capacity allows. So that's why first we need to check that basically the smaller weights array which is there, at that at this index the weight which is there, is that less than or equals to the total capacity. If that is the case, then only we will be taking that value, that is the product ID of the same, and calling our recursive function index -1. That is anyhow we are required to do every time because we have passed that index, and we need to subtract that smaller weight from that bigger weight, because that means that we have taken that smaller weight to put into that particular bigger weight, and now our bigger weight has uh, this much capacity. That is, after subtracting that smaller weight from the bigger weight, now we can accommodate only that remaining capacity which is left. So that's why we are subtracting here, and then weight and value as it is because we are passing as input. So this will be that take case, this will be not take case, and then at the end we need to return take and not take whatever maximum we get from those recursive branches which are there. Because anyhow this base case which is reached, this base case could have reached like in those recursive branches, it could have reached like a lot of times, because we know that when we backtrack, so again, there could be some other leaf node which could be at 0, because what all leaf nodes are there, there could be multiple leaf nodes. So all those multiple leaf nodes, some could be because of the thing that index has reached equals to 0, and some leaf nodes could be possible because of that weight capacity has already reached. So because of all these, there will be multiple leaf nodes and multiple times this case will be reaching. And when it reaches this case, anyhow, it will go to its parent caller. And this return statement also, this will be returned to its parent caller that at a particular time, either if we take that weight or if we don't take that weight out of them, which will give us the maximum possible answer. So that will be the scenario. So that's why anyhow we should be just concerned about that what take and non-take is about, and how the base case is, and returning because we need to return the maximum number of products which are there. So the maximum value which we are going to add here, that is all these product IDs which are there. So as per that only we will be returning our answer. So that will be the whole scenario here. Are you clear with this recursive solution? Fine. Now, because we know that this is recursive solution and there will be multiple branches which could have been already repeated, so there is possibility to memorize the same. And on what basis we will be memorizing it is that this index and weight which are there, so then the multiple branches which will be there, that will be on the basis, because we know there will be at many time it could have reached that zero thing which is there. And even like for a particular same weight, because when we are subtracting this thing, so there could be multiple possibilities where they it would have attained that same weight, and then at that point it is going ahead with the same branching, something like that will be possible there. So on that basis we need to now memorize the same. And here also the only changing things which are there is index and the weight which is there, the total weight with the capacity of that knapsack, those things are changing. So on those things we will be memorizing it. So now the thing, and also here the time complexity will be that exponential, that is 2 raised to power n, where n refers to the size of the weight which is size of the weight array which is there, because either we will be choosing that weight or we won't be choosing that weight. So that is how the time complexity will be. And the space complexity will be, if we just take that recursive stack which is there, where it will be storing that n number of elements, that is the n weights which are there, so that will be order of n, because anyhow we are not storing that number of possible answers which are there, those we are not storing, we are just basically storing the states which are there, not states, basically the weights which are there. So that's as per that the space complexity will be order of n. Now comes the memoized version of the recursion which is there. So now we know what all is changing, index and the total weight, means the total capacity which is there. So everything as it is, what we were doing there, means the base case which is there, that will be as it is. Only new thing which we introduce is this 2D DP into our input also. So here first is index we are taking, and second is the capacity of that knapsack. If that is not equals to -1, then we are returning that, because we know that index and weight both are changing, and there are possibilities that because these are changing, so there are those possible branches which are duplicate. So that's why we are memorizing around that. So now not take also, first we have this not take variable, in that we are whatever we get from this we are assigning in the same, and same thing for this also, here also assigning to the same. At the end, like there at the end the thing is, like here it is the same thing, what all we are doing, we were returning this, now whatever we were returning, now that same thing we will be assigning to this dp of index weight equals to maximum take or not take. So that will let us know that at a particular index with a particular maximum capacity of the knapsack, what was the maximum possible answer, means maximum possible products which we could store inside that knapsack. So like that only at the end we will be able to get, like basically at this particular index, and this particular means the one which was given to us by the question, that at this particular w weight is the total complete total weight which was given by the question, we will be having this much number of products which we can store with this much capacity. So that itself, because of this whole line, we will be getting that answer. So that will be the thing. And now here the time complexity and space complexity, because we know that anyhow the number of weights, that thing around that we are going ahead, means it anyhow forms like a matrix only, that this much weight and corresponding to this much weight we are having we are going ahead with this total capacity of the knapsack which is there. So it will be n cross w, even for the weight and even for this, because we are storing in this. So for that also the space complexity, then it will become that small weight array size into the total capacity of the knapsack which is there. So that will be the same, plus because we are anyhow this is recursive solution itself, so a recursive stack which is there, that will be also storing the n weights which are there plus order of n of that also. So that will be the total space complexity, that is this one and this one. So this is how from recursion to memorization we will be going ahead. But now the thing about that bottom up DB, anyhow there also take and not take things are there, but there's some things change a bit, and how those things are we'll go ahead and check. So anyhow, first thing is about state and second thing is about transition. So what state we need to check and what transition will be. Anyhow, transition is on the basis of recurrence relation which is there. That is these two things which are there, that will anyhow turn into the transition. Now comes the part for the state. Here also, if you see that at a particular moment only index and the total capacity of the knapsack, that was getting changed, because how total capacity of knapsack, what getting changed because of this thing, but that was in a particular branch only, not the complete total which was there. That was at a particular function call and in particular branch. So these things we know which are changing, and that thing will anyhow affect the bottom of DP solution also. So here the thing will be that how the state will be. So state will be here also. We will be having index and we will be having weight. So the state will somehow look like that we are having this thing, that dp of n, that is the weights which are there, and this is again for the knapsack. But at a particular moment, what dp of ij actually means, that is what we need to know. It's basically about the from index 0 till index whatever index we take, that will be our first thing. Basically all the maximum values, basically this line which is there. So our state will be like the maximum value using items from 0 to I with the capacity W. And this W is basically not that maximum capacity which is given to us at a particular given to us by the question. This capacity is at a particular moment what will be the capacity, because it will change as we are subtracting from that total capacity at a particular moment. This line, are you getting it, like subtracting at a particular moment thing? Okay, fine. So because of that thing, our state is like that that at a particular moment, what is the maximum value from 0 till ith index we can attain for that particular W weight which is there. Not that maximum capacity of knapsack, but maybe that maximum capacity of knapsack or maybe lesser than that, because anyhow that knapsack capacity is all we are also getting it changed because of subtracting from that. So that is the reason we are taking at any particular instance whatever weight is there, so till that how much maximum capacity we can attain with the number of items which are there. So because of that the things will be, so now anyhow this is the initialization part where how we are initializing it. So anyhow we are taking n sized n cross w plus 1 matrix we are taking, and we initializing with 0. Then what we are doing is like for weight, from weight of 0 till the maximum capacity of knapsack, we are like whatever at first I had done. So what we are doing is, like if we take this example, this weight is there, the value that is the product IDs, maximum is this, n equals to 3, then anyhow the size of that weight which is there. So now what we were doing with that line was we were just assigning that 0 to this particular row which was all the zeros for the same, and this is the capacity at which we can store, and this is basically that at this index that these product IDs which are there. So what we are doing here is for weight equals to weight of 0, like whatever weight will be there, but anyhow at the starting we have whole of our matrix which is there, that is n cross w matrix, it is initialized with 0. Fine. But next what we are doing is we are starting from weight equals to weight of 0. So here our weight of 0 is basically 2 and its value is 40. So next thing what we did is we basically started from that weight of 0 and we got till that maximum capacity, and we just assigned this at that dp of 0 with this weight equals to value of 0. So basically we assigned all of that with 40. That is the product ID which is there, because we already know that this particular 2 which is there, that is lesser than this 5. But even if anyhow here, because this is that condition, we already know that this weight until then this is lesser than or equal to the maximum weight, we are just assigning it.
For
So
each block, you're gonna check the maximum possible value and then we update it, right?
each block in the sense,
Like if you see in that table, I meant in the table. So if you take 2 comma 3, so for that block, what are all the possible like possibilities that can be stored? Like it can be value could be 30, 40, and 50. So if you get the 30 first, you will evaluate it and then update it to 30. And then if you get a better answer, then you update it back, right?
yeah.
Okay.
But anyhow, like this is that initialization part. So that's why like whatever first value which is there, and it is less, if it is less than anyhow till less than, we will be assigning it. Like we are starting from that first value itself. Then after that we will be going ahead with the next whatever values which are there. And if it is basically like whatever next values, if that give us optimized answer, then that we will be taking. So like that will go ahead. So here also, if you see means the next, the main logic of this which is there, it's like till n weight until the maximum capacity, and anyhow we have already filled that zeroth index, so that's why we are starting from that I equals to 1 rather than starting from I equals to 0. And also other reason is that we will be taking the previous ones which are there also, so that's why anyhow we have initialized the first one, that I equals to 0. So now that when we do this I minus 1, so we can take that previous one also. So from that 1 till n excluding, and then from weight that 0, because anyhow we are starting from that 0 and then going till the maximum capacity which is there. So next thing what we are doing is then our weight which is there, because anyhow we need to check for the weight also, that if it is inside the limit or not. So first thing about not taking means that the present element which is there, that we are not taking. So in that context, what we are doing, we are taking the previous one which was there. Previous one, and that also I minus 1 and W. That is I minus 1 just because it was starting from that 0. Here all zeros are there. Now it is starting from 1. Here also 0 weight is there, because all our weight are starting from 2. Nothing is starting from 0 or 1. So here the thing is like I minus 1, that is I equals to 1, it will become I equals to 0 at that point. And with the weight, what weight we are starting from, we are starting from 0 weight. That is, we are starting from this weight itself. So at this index itself, it will check here also it is 0. So it will here also, for in the not take case, here also it will become 0 only. So basically these all are already 0. So now here also if we take, basically not take will be 0, and if we take, so our take case is take equal to 0, initializing with 0, and then we'll check that weight of I, and now weight of I, that is weight of 1. So here if we see that this weight of 1, 0, and this is the 1. So at this weight of 1, how the things are like, it is 3, 3, and it is already less than equals to the that weight which is there, this weight which is 0. So at that point, this is 3 and this is 0. So this condition doesn't satisfy. So that's why take will be also 0. So that's why here also it will be 0 and maximum out of that will be 0. So like, so now here it will check that out of what is maximum, that will be also 0. So like this, basically the main thing out of this is that if we are not taking, we are basically taking the previous one, just the previous one, that is I minus 1, and weight anyhow remains that only. At that weight, whatever previous we are taking, when basically when we are not taking the present one. And in the case of take, first we are checking the present weight which is there, basically the weight in that array at that index, is it less than equals to the weight which we are counting on? If that is the case, that it is less than equals to, then anyhow we will be taking that value, and value means that product ID, and adding up whatever we have stored at this particular instance. So here if you see, so here lot of because here we are having 40, 50 and 60, but here 90 also is coming into picture. Yeah, only 90 is coming into picture. So it is anyhow after the calculation of this 40 and 50. When we try to choose it, so at that point it became 90. So that is what we are doing is value of I, that is what is our present value, which was 50, and what was previously stored, that was 40. So both of those product IDs we added up here and we got this answer, that is this 90 which is there. And 90 and other was the when we not taking that value, so 90 comma 40 will be maximum out of that will be 90, so that's why 90 got stored there. So all this will go ahead in this manner, and then at the end whatever is being stored at the last, because how our state is like, it is the maximum value using items from 0 till ith with the capacity W. So what we exactly require, we require with the capacity W equals to the capital W which is there, that we require, right? And also index we require. So here it says maximum values using items from 0 till I, but we require all the items, so that means we require till the last index, and our last index is n minus 1 because we are starting from 0 till n minus 1. So that's why here the state which we need to return will be n minus 1 and the maximum capacity, that is the capital W which is there. So that thing when we will be returning, we will be getting our answer because that will be stored here as a state is like this. That's why we need to return answer like this. So I hope you are clear with this. Okay, fine. And here, anyhow, if you see as per the diagram also, it becomes this W is the that capacity of the knapsack, and N is the index, all the indices which are there, that is the weights which are there stored here, and this is that as per the size of the weight array, and this is the maximum capacity of knapsack. So this whole space which is there, that is N cross W, and even on, and it was also like it was 2D array itself, this whole thing which is there, it is 2D array, 2D array and traversing that 2D array. So that's why the time complexity also becomes n cross w, and space complexity anyhow we are storing into the same. So that's why that is also n cross w. So that is how our time complexity is n cross w, and space complexity is also same. Let us see if it works. Fine, it worked. Anyhow, because it's 9 o'clock. Okay, fine. This was a sort of template that this is how algorithm is like. But there will be some scenarios where you need to tweak it, because the way now we are going to do the question, so you need to tweak it a bit, else it won't work. Fine. So let us go ahead with our question. We all You also try to log in to basically try to open lead code if it is possible to log in or not. I guess now it should be
Done, ma'am.
fine. Mm, I guess that was just 1 hour thing only. After 1 hour, we will even solve. Fine. Now for this, now this question is like here also if you see like multiple items are given for a particular product, multiple weights which are given to you. So this thing only I was trying to explain at the starting, but here the thing is that number of items which are given to you, that much number only you can use, not more than that. So now let us first read this question, then try to derive what we need to do in this question, then we'll go ahead that yeah how that knapsack and all is used. So you are given an integer array nums and an integer target. You want to build an expression out of nums by adding one of the symbol plus or minus plus and minus before each integer in nums, and then concatenate all integers. So for example, if nums equals to 2 comma 1, you can add a plus before 2 and a minus before 1 and concatenate them to build the expression plus 2 minus 1. So return the number of different expression that you can build which evaluates to the target. So basically this is just example they have given, that plus 2 minus 1, anyhow plus 2 minus 1 will be equals to 1. So if the target is 1, then this is a valid expression which we can use, and that means that this is one way to attain target 1. Now if we see this example which is here, so here these 5 times 1 is given to you and target equals to 3. Now we need to return that how many number of possible ways are there that we can attain this target. So now here the thing which come into picture is like how 01 knapsack we can use it. It's like that you are given this target which is there, and here these numbers which are there which are given to you. It is also integer array. Yeah. Anyhow, you don't need to return that expression. Only thing you need to do is like you need to find all the possible ways by which you can achieve this target, and how you need to basically have all those possible ways is like either have plus sign before that number or have minus sign before that number, and whatever possible numbers which are given to you, either you use all of them or use some of them, But here, what they have given is you are given this, you want to build an expression out of nums by adding just that thing they have given.
Mom, we have to take all the numbers, but then the tweak is we have to either add or subtract.
Yeah, here we need to take all the numbers. It's not like that at most scenario, but here the thing is about that at most scenario comes into picture as per the basis of either we need to add them or we need to subtract them. That subtract them becomes the thing for that exclusion part, and that also in that sense that we are subtracting it, like either we are adding it or we are subtracting it. Again, it becomes a two-way thing only, that either you add into the same or you subtract into the same. So that is how it, like, it becomes a tweaked form, that 0 1 knapsack, either to choose this particular or not to choose this particular. And if you're not choosing it, then you are basically subtracting from the same. So that is how it is. But here again, it's like whatever numbers which are given to you. So here you will be like, if you're not choosing it, you need to subtract it. If you're choosing it, that you need to add all of them. So like that, all, and after doing all those things, at the end, what you need to check is, you need to check that is it evaluating, means is this branch evaluating to your target or not. If it is evaluating, then fine, you got one expression. Then again, you next you need to try for, means again it's like that, it becomes a tree sort of only. Like if we take that first example itself, now I feel like diagrams are much more easy to explain. So as per the number of ways, we'll see, may not, maybe. So like at the starting, we are given with like 5 times 1 is given and target is 3. So anyhow, when we are starting from this point, uh, basically from this point when we are starting, either we need to choose it. So yeah, we are choosing, so we will be adding, or we don't want to choose it, basically we are subtracting. Then we are at, after this point we are left with these 4 ones which are there. So again, from this also we will be, either we need to choose it or we don't want to choose it, that is we will be doing -1. So here also still, after we have already done with, basically at this point we will be left with these basically three numbers which are there. So again, we choose it or we don't choose it. And here also, if we choose it, if we don't choose it. So like that, at the end, we will be forming some expression. But at each point, we can also check that is it equals to 3 or not. If it is not equals to 3, then fine. We are going ahead. Because here also one scenario will, when we are doing this whole one thing, there could be, anyhow, here it already exceeded this. But here, if we go ahead for this +1, it becomes 5, fine. But here, if we go for -1, it becomes 3 again. So, like if we exceed the target also, still we don't need to block that path. There could be possibility when we are not choosing the other path, when we are not choosing, that is when we are subtracting. So, we could have reached that target because here we reach the target. So, accordingly, our condition will be there that if we are subtracting or if we are adding it up, then it actually reaches the target. If it reaches that target, so yeah, we got our first expression which is there. So that we need to add up. Either in the function calls we need to add them up, or we need to check that do we need to maintain some extra variable which will be getting incremented. So things will be like this. So here it is, anyhow it becomes a form of 0 1 knapsack only. 0 for adding up, and 1 for basically subtracting. And also we have one maximum capacity of the knapsack which need to be fulfilled, and that is our target. Other way to think about it is simply like that it is inclusive exclusive question where we are including, not including, and our main target is to fulfill the maximum capacity which is given to us. So that is how it is like. Anyhow, it comes under 01 knapsack also, and also because the knapsack itself comes under inclusive exclusive type of questions. But yeah, this is the main idea of the 01 knapsack. I hope it is fine for you. Okay. Would you like to try to code it? Okay, fine. But try to code all three types of solution: the recursion, the memoization, and bottom up. Try to do all three. Fine. It's 9:22. Then take around 10 minutes. At 32, I'll ask. Uh, yeah, but before that, could you show me yours recursion code? Like how you have done and why you were not able to do it? Via memoization and tabulation. See, recursion part anyhow it was fine what you have did. So like more precise version of that could be that if sum equals to target, that means it is 1. If it is not equals to that, that will be that 0. So it's that same thing you can write like this, the base case that if I equals to nums dot size, then we need to return 0 1 on the basis of that sum equals to target thing. Then first for the adding and the other for the subtracting. This I have taken like more precise manner rather than taking the take and not take, and things are same. Now comes the part for that memorization, like how we need to do. So basically if you see here also what all is changing, index is changing and this something is changing, that is the target which is there. But now from this how we need to derive our dp state. Our dp state is basically like dp of 5, that is that index which is ongoing changing, means this thing which is there which is changing, and the sum part, that is sum. Here this offset, why we have added this offset is because here if you see in the sum adding part is fine, but this negative part there could be possibility that it would have reached that minus thing to the number of items and the maximum value. Like if you see constraints, so here constraints are like nums dot length is up to 20. That means total 20 items in the worst case scenario will be there for this nums. Fine, one thing is this. Then second thing is nums of I can reach 1000. Mean the value itself that can reach 1000. That means 1000 multiplied by 20, and that will be in that scenario when all the values which are there in that, those all are 1000. Means the way here all values are 1, that could be possible that all the values here are 1000 and there are 20 times thousands are there. So accordingly we need to take this offset value. So if by chance this a whole array comes into picture where all are 1000 and all 20 values are present as 1000, then what will that what maximum negative value it can attain? It can attain minus 1000 multiplied by 20, that is 20,000. Minus 20,000 it can attain, right? So we need to take our offset accordingly. एक मिनट, कुछ तो गड़बड़ है।
Ma'am, is
uh,
it to prevent the negativity,
हाँ,
like
present
to
the
get it
negative.
more?
Yes, because possible value can go negative also. And even what we are doing, this negative thing, from some we are subtracting that negatives which are there. Like we will be subtracting from the sum itself 1,000 times. If by chance a sum itself is zero, say a target given to us is like a target is given to us as zero, and all the values inside it which is there, those are like 1,000, and that also 20 times which are given to us, because here if we see that length is 20, so like it is there up till 20 times basically. This thing what I'm trying to say, that is this nums which is there. And target, that is anyhow from minus 1,000 till 1,000. So yeah, it can be zero also, but what I'm trying to say it, at any point if it becomes, target becomes equals to zero, and we are subtracting this 1,000 from the same, so then at that point the target will be equals to minus 1,000. That scenario also it can reach. And what we are taking this is like the sum which is there. If sum reaches minus 1,000, that is index is negative, that will give us error, right? So that's why we are taking, like if by chance it becomes minus 1,000, then we have something to compensate the same. So that's why we are basically taking this as offset as 1,000, so that we can compensate that particular scenario. But what I am thinking is, because that could be also possibility from 1,000, and that also 20 times, so it can becomes like, simply it can become 20 and 1 2 3, so it can be possible for this also, like it can become minus 20,000. So rather than 1,000, it's better we take it as like 20,000, so that this could be compensated. Are you able to understand this thing?
Ma'am, won't it take much memory though because you have a array of that size?
Yeah, memory thing is fine, but we are having this much only. That is just an, okay. Anyhow, what we are doing here is 20. Why I missed that number? That is what I'm. Yeah, it will take that much array size, because anyhow in the worst case scenario, you can reach like nums dot len 20 fine, but these values which are there, that are also like it can go up to that much sum. That is also one thing. So anyhow we need to store it. But as per the recursion, because see, nowadays we don't have like what we say, we don't have any scarcity of space, but we need everything to be quick. So when it comes to the thing that if we want to take time complexity or space complexity, like which should be higher one, we will go ahead with the space complexity, we can take higher, but time complexity should be minimum enough. But if there is possibility to even optimize that space, then fine, we can do that also. But always we go ahead with like wherever possible we can get the what we say, optimized time complexity. So that is a thing. Hmm. So anyhow, if you see, we are taking this like, because it is till 20, so that's why we are taking till 21. Then we are having this 1,000. So anyhow, it was better if we take that 1001. Still, we have taken that 2001. That is just for the case because we are taking this as 1000, not 20 times. We are just adding it 20. Fine. Anyhow, yeah, that is the case because now accordingly we are taking that 1000 as the offset also. Now comes the next part because anyhow this is for that scenario only, just to negate that, means make that a positive index rather than the negative index. Now things will be same as it is. This also same, that sum plus offset we are taking, and this a sum which is coming from this, and then I which is coming, that is this. I guess you were confused in this part only, that how we need to take it, means I or sum minus
Mm.
1 or what, right?
Yes, ma'am.
Hmm. So basically as it is, whatever we are having here, means whatever we are passing, same thing we will be taking here, and whatever we are passing, same thing we will be taking here. Here we have added offset just for the part that it doesn't become negative and it gives us error because negative index doesn't exist. And then if that is not equals to minus 1, then we will be returning same as it is. Then that add and subtract thing which you had done, same thing we need to do here also. And then at the end, this add and subtract, that same thing we will be just assigning to the same. So that is what we are going to do. And that is how,
So the number of possibilities is stored in the table.
yeah,
I got confused with the sum. I thought we have to store the actual sum and then traverse it again. No, that was
knapsack becomes confusion because of this thing only. When at the starting I was also doing knapsack, I got confused with those values and weights. I was like, what they exactly want. Then I thought, no, values are basically those product IDs. And here also it's like weight, and then we need to store the number of possibilities. And weight should be the parameter for determining that it is, yeah, less than the target. In every question, it will be same.
okay.
Wait, hmm. Okay, now the next thing. This is about that bottom TP which is there. So here till now what all we were doing? We were just assigning plus to a particular number, minus to a particular number. So now bottom TP also it will be around this, but now we need to determine what is state and transition. Here if you see the recursion is something like this, that we are just adding that number or subtracting that number from the target and calling our function again. So here the things become like, if we basically like uh, devise some equations from the same, things becomes much more easier, because it's like if you see here there are two things, either we are assigning plus sign or we are assigning subtraction to the same. So here p equals to sum of numbers with all the plus signs which are there, that is positive numbers, and these are the negative numbers with all the negative signs which are there. So if we add both sides, so it will become like, not add, that thing will be here. Now if you see all the positive number, if we basically subtract from that all the negative number, that will give us the target. Like if we have two subsets around that, where all the positive numbers are such that and negative number are such that we are getting a target, because anyhow we are required with a target, and we need to assign those positive and negative number in such manner only. If you see this scenario, all the positive numbers which can be possible and all the negative, that is only one which is here possible. So if we basically the way they are, like that only we have them, that is positive with plus sign, negative with the negative sign, have them, then we are getting our target in the positive scenario. If we add both of them, then we will be getting our total sum. Because if we take all the positive numbers and even all the negative numbers as well, and if we just add them up, we will be getting our total sum. Here we are just having the numbers which are then just number without their signs, just number. That is all the ones, and the one which is there with a negative sign, but we are just taking that number. In that sense, if we take and then if we add both side, so these will anyhow get negated, and we will be having p, 2p will be there, and these all are so added up and divide by 2. So the problem then becomes that count the subset with the sum equals to p, that is sum equals to this all the positive numbers which are there. And if we see here, for getting this p, what exactly need to be there? It's like this target and total sum which is there. When we add them up, it should be divided by 2. So for getting this thing to be like perfect, that it is divisible by 2, in that sense, this target means the sum which is there, target plus total sum, that should be even. Then only we can divide it by 2. That should be one condition. So that becomes one of our base case. Another thing which is there is the target should be less than or equals to total sum. And that also the mod which is there. Because if by chance it becomes negative and we divide by 2, that also is not a thing which we can do, like p equals to minus something. And p is actually the count, and count can't be negative. So this condition should also be valid. So these two becomes our base case. Now the first thing when I was doing this question, I was like, okay, even if we come to this conclusion also, like how this p is the only one which we need to find. So if you see, like, anyhow we need to have all the numbers which are there to be equals to target, and we know all the numbers which are there that add up to a total sum. These two things are there, so accordingly these conditions will come up and it will give us the answer. That is how this comes into picture, these two equations. So that's why, like, at the starting also I was trying to convey, like, somehow bottom up dp which is there, at some scenarios it will be good to get into that, but in most of the scenarios it will be like you need to have some equations also, or you need to think much differently than what you have done in recursion and memoization solution. So like here also it was more like that you need to derive something, and for that, then after that you will get to your bottom of dp. Like after this thing, now it is easier to go ahead with the bottom of dp. So now because you know that you need to just count the subsets with sum equals to p, that is all the positive ones which are there, with that itself you will be getting your count of the expression. So for that, how your state should be. So state is like that at a particular state, that is dp of s, we will be basically having the answer to number of ways to form the sum s. And then initialization dp of 0 equals to 1 means anyhow it is 1d dp, not 2d dp. So because of this equation itself, we earlier our space was like 2d in nature. Now our space is just 1d in nature. And then the transition which is there, so transition is like we will be just adding up all the sums which are there which we got before also, that is s minus num, and we will be adding that up to our present one which is there. But here it will be a backward loop which will turn out to be like whatever which we have already stored in the future, that all we will be getting in our present one. So that is how our transition will get changed, and this is something which will give us answer for adding up and subtraction anyhow, that we are taking care in this thing which is there. So that's why it's like that two subsets gets created, one of the positive and one for the negative, and now we are just concerned with those that subset which has all the positive numbers into the same, Because if you see, like all of these numbers which are there, these have positive and negative both combinations are there. So now we are, and anyhow we can get that expression even with that positive, even with that subset also, which has all the positive numbers. I'm not saying that adding up all of this will give us this target. I'm not saying in that sense. What I'm trying to say is, like there a particular expression which is there, it will be having positive also and negative also, right? So why we are like, why we should be concerned with the negative at that point? It's better we just concern about the positive one, because positive is also giving us that expression, means positive is also part of that expression. So that's why rather than counting that positive and negative both, which actually makes more branches, it's better we count only for those positive ones which are contributing to that expression. Because the way this thing is there, by using this thing, now we are basically subdividing our problem to much smaller problem, that is count subsets with sum equals to p, and that p is equals to target plus total sum divided by 2, rather than counting all the expressions which are equals to target. So that is the thing. Are you clear with this boiling down to a sub problem?
Somewhat, but how do we analyze all of this in the interview?
Yeah, that is the thing. That all comes with the practice only. Like you more practice about a particular pattern, you will start getting it. Yeah, we could do it like this also. Like when you have done this question, then there is one more question which I'll give you. And when you have done that question, if you've done both those questions, there is one third question. And that third question, you will automatically get that, yeah, this is similar to what I have done in the previous two questions. So it's like more you practice, you will analyze, you will be easily to analyze it. Like this is first time you seeing this question, and first time you are getting that, yeah, this could have been done like this also. But yeah, more you do practice, you will get. So now accordingly, because we are now concerned with this part only, so accordingly we need to do here. So first we need to find a total sum. Total sum anyhow we can find like this, mean looping around all the numbers which are there. And other thing which we need is target. Target anyhow we are already getting. Now next thing we need to do is we need to do this thing. And before doing that thing, we need to make it possible. Like we need to make sure that target plus total sum is even, so that we can divide by 2, and also this thing is also there. So that is what we are doing. First thing we are checking that absolute of target is basically greater than total sum, if that is the case, or if this target plus total sum modulo by 2 is not equals to 0, then we need to return 0. Because if both of these scenarios are not possible, then going ahead is not possible. That means we can't form any expression. That is the thing, because we got to know that if this is true and this is anyhow true, and this is, if this is true, then only we can get this, right? So that's why these things should be true. And because of that, if these things are basically this thing is that false scenario, unhappy path, if this is the unhappy path, then we need to return 0. So that is the thing. Now we have already a base case. Now next thing comes into picture is that we need to calculate this p value. So p value we know we need to calculate like this as per the equation. So that is what we are doing. And then because of all this scenario, now we got a state something like this, that dp of s equals to number of ways to form the sum s. And that's why it is a 1D dp. So that's why we are having this dp with p plus 1, because we require it with this p, means count subset with sum equals to p. So that means we will be having the number of values which are there, that will be p plus 1 here, all initialized with 0. And at the starting we are initializing dp of 0 equals to 1. That means if rp equals to 0, that is sum equals to 0, then also there is one way to write is, that is one way, the 0 sum itself. So that's why dp of 0 equals to 1, because here we are storing the number of ways. What we are doing is number of ways to form sum s. So number of ways to form sum equals to 0 is 1, right? So that's why we are initializing it with 1. Then comes the part that these numbers which are there, which we are taking from the same, and then for int s equals to, that is our sum starting from s equals to p. And then here one thing which we need to keep in mind is we need to do a backward loop rather than doing a forward loop. If we do a forward loop here, then it will become a unbounded knapsack. Here we need to do a backward loop, and that also it's not like you need to cram it, it's like there is a logic behind it why we are doing it. See, uh and okay, that will go later. First let us go ahead with the main logic which is there. That is, we are starting from the highest, that is the target itself, and we are going, because we are choosing this num which is there, we are having this starting from the target and going till the num which we have chosen, that is this s. If it is greater than equals to num, till that point we are going and subtracting that. So first whatever our target is there, so in that target we will be adding up at any point. If we subtract that s minus num, that is whatever our target at the first point, whatever our target, and subtracting that num. If somewhere whatever we get, if we have somewhere stored that, this is example, so that we will be adding up, and at the end we need to return dp of p, because what we are doing is our state is like dp of s equals to number of ways to form some s. So now what we want is number of forms, a number of ways to form some p. So that's why we will be returning this. So that is what we are doing is now the example part. That is, if we take the first example itself, where nums is like this, target is this, and total sum is 5. So 3 plus 5, 8 by 2, that will p will be 4. We got our 4. Now we will be initializing it like this. That is at the starting 1, and then all are already 0, because at the starting we initialize it with 0. But at the starting, to get the sum equals to 0, we have one way. So that's why we initialize with 1. Then our first term equals to 1. That is this one which is there. Now s equals to 4. Here if you see s, we are starting from p, that is 4. So dp of 4 equals to plus equals to dp of 3. And how we got 3? That we got by p minus num, and our num was 1. So 4 minus 1, 3. So we know that dp of 3, that is 0, 1, 2, 3. This is also 0. So that's why here we add up 0. Then dp of 3 plus equals to dp of 2. So 0, 1, 2. It is also 0, so 0. Then we decrease it, and dp of 2 plus this, and then dp of 1 plus equals to 0 equals to 1. How? If you see, this is 0, this is 1, and dp of 0 was 1. So now because of that we got dp like this. And then when we go to second number, now same thing will come into picture, that same scenario. So now here what all is happening is that whatever we would have already stored, that is getting stored in our present number which is there. So like whatever was already stored, so that only we are storing it. It helps us to use all the numbers at most once, rather than basically having it more than once. So exactly at the end when dp4 is there, so we will be getting 5 as the answer. So what exactly we are doing is, so every way that previously made sum s minus sum can now make sum by including num. So new ways to make s equals to old ways plus ways including num. But this old ways which are there, there could be possibility that we could have counted basically something which was counted more than once if it was a forward loop. Like if it was something like this, instead rather than doing it like this, if it would have been something like starting from the num itself, like s equals to num and going till p, then in that scenario it will be like we are choosing a single number multiple times. And that's why we are doing a backward loop. That is, we are starting from dp of 4 equals to, we are starting from whatever was previously stored, so that only we are assigning to our the upcoming which is there, rather than going from this one and whatever is being stored here that we are assigning to this one. Rather than that, we are doing whatever is here, we are assigning that to this one, so that only once everything gets added. Because if we go in like whatever is in future and if we assign that to this particular, then it will become like that we have not even reached this particular point, and it is something which we got from somewhere, and we are just adding it up, and we don't know that at that point it was like more than the required capacity, means more than the required supply which is there. So that's why here we are having a backward loop which actually does that whatever we are having previously stored, that gets add up to our present one. So that is the thing. Maybe this bottom up and also this particular scenario, maybe it becomes, maybe it does, I'm not sure that are you able to understand it or not.
Somewhat.
Okay, fine. Maybe when you'll do that unbounded knapsack, then you'll understand it more better. But it's like this only, that we need to store whatever is at the previous ones that need to get stored to our present one. So that's why we are doing it like this rather than doing it other way around. Yeah, when we'll start with that zero one, sorry, unbounded, you'll, when you will having those contrast examples, you'll understand it more better. But at least the main logic which is that you are clear, right? Fine. And now here time complexity is n into sum. Now here the time complexity part, even if it became 1 DDP, but still time complexity we were not able to reduce it, because anyhow we need to see all the numbers and we need to target that target sum which is there. So accordingly we need to have a loop. So that's why time complexity here was not reduced, but anyhow space complexity got reduced because of those equations which were there. Else the space complexity would also be like you are checking all the sums which are there. So that is the thing. So this was for this particular question. I'll give it next question then.
Excuse me, ma'am. I actually have to go out at 12 o'clock. So is it fine? Can we reduce it to 12?
We got those subsets which were there, right? So first let us read the question, then we'll conclude that how we need to do and how it is similar or different like that to the target sum question which is there. So here, given an integer array nums, return true if you can partition the array into two subsets such that the sum of the elements in the both subset is equal, or false otherwise. So basically the integer array nums which is given to you, so you need to return true if you can partition the array into two subsets such that the sum of the elements in both subset is equal, or false otherwise. So now here if you see, although target is not given to you, in an knapsack always target is given, but here if you see this question is somewhat similar to previous one when we had those equations and all. So it anyhow boiled down to that we actually require two subsets, one of the positive and one of the negatives. That was about the previous question, that is the target sum question which is there. But now here no target is given. Only thing, only information which is given to you is that you need to divide these to two subsets, and those two subsets should be in such a manner that first subset and the second subset, both sums should be equal to each other. If that is possible, then fine, you are good to go and you need to return true, else you need to return false. So now here if you see, like again, first thing you will be doing this thing only, that you will be checking that if I have these in this and these in this, then what is the sum? Means you will be basically trying to check out all the possibilities, that if I add this number, not adding in the sense of that I'm basically adding itself, that plus sign thing. If I add this number 1 and then 5, if you see this sum and this sum, basically the number itself, both of them becomes equals to 11 only. So that's why we are returning true. But before coming to this particular, you will be checking all the possibilities, that if I add this particular number to my this subarray, does it actually becomes equal to the other subarray or not? Like that only you will be checking at each and every point. So basically again it will become a recursion tree to choose it or not to choose it, so that at the end we can get our what we say, we can get our sum. But apart from that also, like, I don't want to speak too much, let's just have diagram and explanation. So basically the question is like that you need to return true basically sum by 2, that is the total sum by 2, you have two subsets basically equals to. That is the question about. Else you need to return false. That is what this question says. Now if you see, although they have not given us target, basically no target is there, but the question says that both of these should be equals to each other. That simply means that what we need to do, we need to do total sum and just do by 2. And this is how it becomes our target.
Ma'am,
Hmm?
ma'am, do we have to include all the elements or can we take any subset, like two elements, just two?
Include all the elements in the sense.
Ma'am, in that case, like the first example, we have 1, 5, 11, 5, right?
Hmm.
So can we take only the 5 in the second, what is it, index and then the fourth index? So you can say that there is a combination wherein the subset is equal and then return true. Or do we have to include all the elements like 1, 5, 5 and then 11? Like they've given one of the example as 1, 5, 5, 11, but is it possible that we can just take a small part of the whole array and then
They
equate?
have told that we require, uh, like, see, here in the question, they have told that whatever is given, fine. You can partition the array into two subsets such that the sum of elements in the both subsets is equals. Then basically the whole array which is there, that you need to partition into two subsets. So in that context, you need to take all the elements. That will be the thing. Like like whenever you have such doubts, not just try to basically what you need to do, like this is given to you, right? That scenario where we can skip, that could be this thing. uh, we can take this. So now here, if we skip one, right, so still we have that we can divide this into two subsets. But again, here itself you see, it won't be two subset, it will become three subsets actually. That is 5 and 5, this 5 and 5 and then 10 and then 1. So that it violates the question itself. That will be the thing. So we can't take it. We need to take all the elements and divide them to two subsets. So because of that, uh, that were the thing. We need to use all the elements. And other thing, target is not given to us, but it says that both of the subset sums which are there, that subset 1 sum and subset 2 sum, those should be equal. And that will be equal in that case only, that if we do total sum of the whole array and divide by 2, so that becomes a target. In that case only it is possible. So that's why now we know that our target which is there, that is equals to total sum ts by 2 basically if we say. Uh, hmm. That is the thing. Fine. So we got a target with this. Now comes the part. First thing, just think in recursive manner so that you can memorize it after that. But before that, how it becomes knapsack, it's like either we need to, like this thing which is given to us 1, 5, 11, and 5. So it becomes like either we need to include it or we need to exclude it. And now this inclusion exclusion which we are doing this, like whatever we are including, that will go in our subset 1, and whatever we are excluding it, that will go in our subset 2. So it becomes like that. Like the same way our target sum which was there, it was like we are assigning plus or minus. So whatever we are including in plus, that was like a subset 1, and whatever we were excluding, that becomes a subset 2. Means one we are including, another we are excluding, and excluding from our subset 1. So that's why if we are excluding from subset 1, that by default falls into subset 2. So this inclusion exclusion was for a subset 1 scenario only. So here also, if we are including, so yeah, we got 1 here, and here we got 5, 11, 5 only. This is our subset became. So now at this point, we are left with 5, 11, 5 for this whole. So now here also, if we go ahead, now if we include 5 also, so now it becomes 5, and here it becomes 11 comma 5. This is for the including part, and this is for the that excluding part which is there. And same here. Now we go ahead. So here if we include 5, and here we will be having 11 and 5. But now again the things comes into picture, like where one has got. So in that scenario also, the way we need to write our code is like we have those two subsets, so that all the elements are included. So now here out of that, if we include 5, so 11, 5 will fall here, and also the 1 itself, because anyhow 1 was left here and we need to have all the elements included. So our code should be also in that manner that at each point we are having those two subsets which are there. So that will be the scenario here also. Now here if we go ahead, so 1, 5, and next thing which we are required to include is 11. But here now we are left with just the last 5 which is there. And here 11 and 5. So if we include both of them, and now at this point we were just left with 1 and 5. So like accordingly now whatever one of the element we will be choosing out of them with which we were left. So 5, 11, 5, and here we were left with 11 and 5, and here we are left with just 5. So 11, 5 we included here, but the other element, that is 5 and 11, the starting 5 and 11 which was there, so accordingly we need to choose them also in one subset, and the other one will be having that other which is there. So that is how our tree will start forming, and we need to like include in one subset and exclude from the one subset that falls to the subset 2. So that is how we will be going ahead, provided that at each point we will be also checking. Anyhow, we know for this it is equals to 11. So we will be also checking that does it equals to 11? No, fine, we'll go ahead. Equals to 11? No, fine, we'll go ahead. It is greater than 11. So anyhow, this is excluded, and this is basically less than 11. Fine, we'll go ahead. So like that, we will be anyhow having our base case, which will let us know that if this is equals to the target sum, that is total sum by 2, which we will be already calculating. So basically the whole thing boils down to the same the way we were doing earlier. Only thing here is that we need to check if both of them are equal or not. neither subset 1 and subset 2, whatever we are getting there. So if they becomes equal to the target or not, both of them basically. So that is how the thing will be. Because I need to leave you at 12. Would you like to code for 5 minutes? Fine. Fine is 10:27. Yep. So 11, 11 2. Then you just code it. Even recursion is also fine. Then we'll discuss about the memoization and that bottom up. So here we need two subsets where target sum is equals to total sum, mm, total sum by 2. So here in total sum equal to 0, we are taking that total sum. Then first we are checking that if total sum modulo 2 is not equals to 0, then we need to return false. Because in that case, it will be like we can't even have two subsets whose sums are equal to each other. So that is one of the base case before going ahead with the recursion. And then we need to call our recursion by starting from index 0, our target sum, that is total sum by 2, and nums array on which we need to calculate. So first thing, if target equals to 0, we need to return true. That means we have already reached that condition. And then if I equals to nums dot size or target is less than 0, we need to return false. That means that we have already reached, means our array is exhausted or a target becomes a negative. So that simply means that this is those scenario where two subsets having same sum not possible, because we have already exhausted and also or a target is less than the required one, because anyhow we are also negating and we are at some point we are negating it, at some point we are including it without negating the same. So that's why at that point we will be returning false. And that is how, like, either of this or this, means including, excluding, we are taking it. So that is what we are returning. So this is how our recursion goes in. Now comes the part that how we need to memorize it. So for the memorization means our state will be like the dp of I target equals to -1, that is unknown initialization part, 0 for the false and 1 for the true. And why we are memoizing? Because we know that I comma target, that same state repeats many times. We know because there will be multiple branches which are duplicate. So that's why we are memoizing. So now everything will be same as it is. Only thing is like whatever we are taking this thing, that is because we know that this index which is there, that will go till 200. 201 we are taking one extra because 0 till 200, so it becomes 0 is in one extra thing which is there, so that's why it becomes 201. And then the value, that is 100 which is there. So now this 100 value multiply by the number of times it is, so accordingly it becomes those and 1. And even in that scenario also, like even if we multiply it, it becomes 200 and 100, it becomes 2000, sorry 20,000, but still we are taking not we are taking, yeah, that only one 10,001, just one extra we are taking. And also one more thing is there, like rather than taking this thing, we could have taken just direct vector or vector int and initialize it with the nums which is there. But in that scenario also, the thing will be that there could be possible that anyhow num initializing with nums dot size, fine, one thing is taken that yeah, we will initialize with num dot side, that will take care of this. But the value part which is there, that value part anyhow we need to take care by that what exactly maximum value it can go. So that thing we need to anyhow take care. And also it is sum, So accordingly, there could be possible that this 100 which is there, that is added up 200 times. So accordingly, we are taking this thing. So that's why it's starting, it's good that at the starting itself, as per the constraint, we have these values there rather than initializing it as per the size of this nums and then the value part which is there, that is the target sum part which is there. And then this memset dp is basically that initializing with -1 as per the size of the dp, that is this whole size. Basically this whole 2D array which is there, that will be initialized with -1, and then we are just calling it same. Then whole thing will be same as it is as recursion. Only thing which got changed or added is we added this line that if dp of I target is not equals to -1, that means it has either 0 or 1, then we need to return this dp of I target as it is. And the other line which we added for memoizing it, return dp of I target equals to take or skip, that is this take or skip, which earlier what we were doing was we were just returning it the whole function call as it is, that is the take or skip thing which was there. So that is how it becomes a memoize solution. Now comes the bottom of dp part. So for the bottom of dp part, now here the dp definition, that is the state which is there, that will be that dp of s that is true if subset s is achievable, like the memoization part which was there. So here memoization, we were memoizing it means our dp state was something like dp of I target which was having either true or false as per 0 or 1, means 0 for false and 1 for true. But now here we are storing true or false on the basis of that. Now here what we are doing is rather than having that index and means there were we were having two variable being changing. Now here that two variable changing we will take care in a separate manner in this bottom of dp. How we will be doing here is we will be now considering this sum which is there. Is that sum achievable or not? That subset sum which is there, is that achievable or not? That we will be storing at that dp of s. Anyhow that sum will be changing as per the index which is ongoing. Then dp of 0 equals true, that sum with sum equals to 0 is achievable, that is initialization part. And here transition will be like dp of s or equals to dp of s minus num. Again that backward loop will be followed, means similar to that what we were doing earlier. So here basically the thing will be like that first we will be having our sum so that we can get our total sum by 2 thing. This is base case, then our target. Till this part, everything is similar what we did till now, because this is like that mathematical thing which we require. Same. Now, the next thing is there is that 2D thing that yeah, we will be storing at a particular just target. We are not concerned with changing index. That we will be handling in this itself, in this loop itself. What we are trying to do here is again the same loop we will be doing. S equals to target and S will go till num, and the same logic will be there, the thing which we were using earlier in this thing. I mean same thing will be there here. Anyhow we were adding up, but here what we are doing is here we are checking if dp of s is true or if dp of s minus num is true, like whosoever is true, so that will get assigned to the same. But anyhow at the starting everything which is there, that is false only, but if either of them becomes true, then that will get assigned to that sum. And then dp of target anyhow will get the answer that yeah it is true on the basis of this boolean things which are there, means boolean or thing. So again it's like same thing which we used, but now rather than having that index thing which is there, we are using the sum which is there as it is, and we are trying to figure out that yeah from this 0 till this index whatever numbers which are there. So here the only thing is like earlier what we were doing was we were having all the indices and accordingly index we have passed and then we have this target sum, from that we were subtracting. But now here what we are doing is we are having a target sum and that target sum is getting incremented every time from basically target some, and then it goes till num, although here it is getting decreased till that. So that index part which is there, anyhow, that is already taken care with these two loops which are there. Every time we are choosing a particular number, and that number we are going till that, from the target till that number, and we are checking that if anything was there already stored for the same as true, then we are basically doing that bool thing with the same, means sorry, or part with the same, and then accordingly we are getting our answer that yeah, it is possible or not possible. Means almost similar to what we were doing earlier. Only thing is like earlier it was that addition, and now we are having GOR. And time complexity and space complexity also, that will be also same as what we were having earlier for this bottom up. And even for others also it will be same only. Means other three which are there. Now it's 11 o'clock. So let us start with that unbounded knapsack. So anyhow, I hope this works. Okay. Anyhow, for that unbounded knapsack at the starting, I told like what is the difference between an unbounded knapsack. That is only this thing that it has now the infinite supply of the items which are there. So that is the only difference between both of them, unbounded and 0 1 knapsack. Else the whole thing, like we have a container and we have some items and we need to put the items into that container optimally. That will be the only thing. But with that, we have just infinite supply of those small items which are there. So now first about the template of this unbounded knapsack. First thing, that weight of I, value of I, find these things the same as what we use, but the only thing is that you can take unlimited copies of each item. That is a thing. Now how we need to do in recursive manner. Earlier it was like that fine, we have this much supply and we can use this much, but now it's only purely based on the like how much target which is there, like are we able to achieve that target with the help of that much amount or not. Now here, take it, stay on the same index because it is unbounded, and skip it, that is move to the next item. That is where things change. Now here I equals to weight of I. Now here we are taking basically that I from the 0. That's why when I equals to weight, weight dot size, or capital W equals to 0, then we need to return 0. So not take condition is like not take, that means that we are not taking this one, we are passing it. So that's why then only we are increasing that index and everything remains same. And in take equals to 0, so that will be like if weight of I less than equals to that capital W, then in that case only we will be subtracting it. But if you see here index which is there, that remains as it is. Here we are not passing to next index because we can take a particular item any number of time, provided our knapsack capacity which is there, that is still there to have that item. So that is the only determining factor in this particular, else everything is similar to what was in 0 1 knapsack. Only thing, if you see, only thing which got changes, that here now we got here we got anyhow this was also same to what we were there using there, but here we are starting from the starting rather than starting from ending. There we were starting from ending. But that is anyhow The form, basically the way to do things, that is a different thing. But the only thing which got changed here is that here we are not incrementing that index or decrementing that index. We are not passing, we are again and again choosing same element. That is the only difference. Else everything is same as it is what we were doing earlier. Here base case got changed because anyhow we are starting from I equals to 0 and not from I equals to n. But other thing which also got added is that weight equals to 0. Earlier we were not having any condition about weight. We were just having this condition that it should be less than that weight, then it's fine. Else we are not going ahead with that. That was the thing. DP, this will be same. Hmm. So only this thing is different. That is this weight equal to 0 condition, or this thing which got added. And also here I plus 1 or I minus 1 is not there. Just for the fact because we can choose n number of items. So that is the difference between unbounded and 0 1 knapsack. Now this thing is fine. Now how we need to memorize it? Again here index is changing and weight is changing. If you see here, here index is changing and here weight is changing. Fine. So that's why DP we need accordingly. Yes, Tuti.
Ma'am, even in this, we don't have to do the descending
Yeah,
part, ma'am.
yeah, here also we don't need to do any descending ascending. Whatever
Ma'am, but
is,
then we get the maximum value if it is descending, right? Like starting from what do you say, the maximum value which we can get, we'll store it first in the knapsack and go along adding the values which are lesser.
see, that maximum value or smallest value, that all part comes under greedy. That this is the maximum we can store, and then accordingly what all others which are there we can have it. But there could be possibility that rather than choosing that maximum value, if we choose that second largest value which is there, that can give us more optimal answer. So that's why here we are not storing either in descending or ascending. Here we are trying to think of all the possibility in random orders. So that's why we are having it like that. It's not having any sorting in place. Now here for the memorization, again we know that what all are changing, I and W are changing. So accordingly, our state will be like dp of IW equals to maximum value we can attain at that point. So now this is just like that taken 101 and 1001 just for just like that for say for example. The constraints are like that we need to choose it like this. So same thing as it is, the thing which we usually put for the memorization so that we can use that rather than going to a duplicate branch. Then in not take and int take thing which is there, fine. But at the end we just need to assign whatever maximum we get out of them, and this will be all same. Basically the whole recursion part, memorizing it refers to this and adding this in this scenario, that if that is already stored we will be using it, and we are basically storing when we are returning it, so at that point we are storing it. So that is how we need to do. So now comes the part for the bottom up. So bottom up part, here this is a basically in the top sorry, in the 01 knapsack, what we were doing were we were doing a backward loop. Now here we need to do a forward loop. That is the only difference here which will be there. So again 1D dp also, here also dp of W equals to maximum value for the capacity W. Same thing the way we were having in the 01 knapsack. And transition, that will be also same as it is what we were having there. But the only thing is the loop part which is there. That will be, earlier it was backward, now it will be forward one. So that we can have whatever in the future is also stored, that also we can have in our present one. Like multiple times we can use a particular number. That's why here we will be having that forward loop scenario. although I guess in this you won't be able to understand that much. Once we'll do some question there, you'll understand. So here it's like same thing, starting from that index and then for the weight, because index and weight are changing. So we are starting from the weight of I, that is the starting weight itself, and going till the maximum capacity. And there it was starting from the maximum capacity and going till the present weight. It was like that. And then out of them, whatever is maximum, that is whatever is stored in the present one. Or if we take the value plus whatever is there stored somewhere else, that is at this point, means when we do weight minus weight of I, that is when we choose this weight and subtract from the same, at that point whatever is stored plus our present value, that is this. And whenever we don't want to take our uh, present value which is there, and whatever was already stored at this part, maybe because of some other because anyhow, because of this thing also, you are storing to some other place, right? Because w minus weight of I will make index as something else, that is storing at some other weight. So again, at this point also someone else would have stored something, so that only we are including here, rather including the value itself. When we are including the value, when we are doing value of I plus something which is stored somewhere else. So out of them, whatever will be the maximum, that will get stored in dp of w, and at the end we will be returning the dp of the maximum capacity of the knapsack. So that will give us the maximum weight which we can basically maximum number of items which we can store with this much capacity. So that will be the thing for this unbounded knapsack.
Ma'am, is there a scenario wherein we take the item one and only the item one is stored in the knapsack, no other item?
See, in the knapsack scenario, it's like that we need to have maximum number of items. And yeah, there could be scenario where we are just storing the one item, that is the first item itself. When all the other items which are there, those are basically having the weight which is greater than the target weight. Means say uh, the target weight is 5, mean the capacity of that knapsack itself at the starting itself, the input which is given to you, that is 5. And all the weights which are there, that are like 1, and then all other are 6, 7, 8, 9. So here in this scenario we will be just storing that one itself. But here it is like 0 1 knapsack, so that's why in that scenario you will be having like that one itself can be multiple times stored. So there the answer will be 5 itself, with the weight 1 and 5 items, because 5 into 1 will be that 5 weight total, which is the capacity of the knapsack itself. So this is that scenario where it could be possible, means it is possible. And this one I told for unbounded. And if would have been 0 1 knapsack, then there also this scenario will be there, but there only one item is there because it is 0 1. So you have limited item, that is that item only one time you can use. So it will be one item with weight 1, and all other won't be included. So that will be the thing. Okay. Is this clear? Okay, fine. Anything there? Why it is having that? पता नहीं क्यों है. Fine. Uh, Let us go ahead with the next question for the unbounded knapsack. We have two famous questions, coin change, that we will be doing. Both of these are unbounded knapsack only. We'll do first one. Second one, not sure if we will have time to do that. That will do. You can do as homework, or else I'll explain and we'll do. 1 minute. So, uh, you are given an integer array coins representing coins of different combination and an integer amount representing a total amount of money. So, return the fewest number of coins that you need to make up that amount. If that amount of money cannot be made up by any combination of the coins, return -1. You may assume that you have an infinite number of each kind of coin. So that means that this is unbounded knapsack. And also there is some target given to you, and there are few smaller weights given to you. So that becomes a knapsack problem. And when they tell you that it is infinite number of each coins, that it infinite number of those smaller weights which are there, that becomes unbounded knapsack. So accordingly now you can do this question when you see all these lines and all these direction given to you. So now if we go ahead about this question which is there, like what all given, so on. Okay, they told that infinitely we can use each coin, and we need to complete this target amount, that is 11. Means our knapsack capacity is 11, and we can choose like and one more thing which they have given, means which they want us, return the fewest number of coins, means minimum number of coins you can use, that you need to make up that amount, that is this 11 amount. If that amount of money cannot be, then -1. Now here it's like not the maximum number of products, here it's like minimum number of products you can use to make up that value. So that when it's about that minimum number of products to be used for that for that capacity, means knapsack capacity, then surely we will be trying to, anyhow, in general sense, like greedily we think about, it will be like we'll sort it in descending order and we'll choose all the bigger numbers which are there, and that's fine, we can go ahead with that. That is if we think about it greedily. And also we can choose like any number of coin any number of times, that is also one thing. But in that scenario also, if you think by choosing that greedy manner, it could be possible that we are missing out with some minimum possibility to reach that that knapsack amount, there could be possible. And that is how, like, say, like anyhow the way this example is this 5 plus 5 plus 1, we are getting 11. But if by chance there are some because we want minimum coins also. Mm, I'm not able to think of that scenario. But see, like if we are given with 2, and say rather than 6 and 6, means say 6 and 6 is not given, we are given with 3, 4, 2, and 1 is given to you. Say, these all are given to you. So we need to make up 12. If we choose all ones, means 1 multiplied by 12, if we choose, that is so many coins. Fine. If we choose 4 plus 3, that becomes 7, means anyhow we just need to add up to 12.
Ma'am, are we doing more number of coins or maximum value?
Maximum value, and that maximum value should be 11,
Okay.
but minimum number of coins. Okay, but does actually one thing is that at starting it confused, means when I was doing it that time it was confusing me also. It's like number of coins, that should be minimum, and the value which is there, value should be equal, means less than or equals to the amount which is there. This is the question about.
So we are supposed to give importance to the number of coins itself, not the value, right?
Basically we need to give importance to both of them, in that sense that we are able to achieve this amount, but with the minimum number of coins. It's about comparing the weight with the weight, but the products which are used here, that should be minimum.
Minimum. Okay, ma'am.
That is the question about. Um, okay. Yeah. So in this whole scenario, anyhow, in the first one, it's like that we are taking these biggest values and then we are having this one added up. So it became 11. Fine. Then here only 2 is given and 3 is given. So there is no possibility even if we do like this, it's not possible to achieve this. And even for this, it is how? Coins equals to 1 and amount equals to 0. How it is output equals to 0? 0 means that anyhow amount is 0. So yeah, fine. We if amount is itself 0, then there is no coin which can give us that value. So yeah, we are returning 0. But if there is like some other amount given to us, then we need to return -1. Yeah, it is not possible at all. Amount 0 is like not choosing that coin and getting that amount. That's why we are having output as 0. Any other example? Although I'm not able to think for time being, not able to think of any other example, but fine. Yeah, even this example which I was telling. So one possibility 1 into 12 coins, then other possibility say 2 into 6 times we are taking all the coins, other possibility 3 into 4 times taking all the coins, 4 into 3 times taking all the coins. These are few of the possibilities. But if we take like here it's like this is the number and this is the value of the coin. This all are base already equating to this 12. Fine. But other possible way like minimum out of them if we see that is this one, not this one, sorry, because this is number of coins. Hmm. So if we see out of them, the minimum number of coins is used here 4 multiplied by 3. That if we take 4 coins 3 times, we will get this 12 answer. But is there any other possibility that we get this 12 even with much lower thing? In that sense, if I think I.
If you take minimum, then no. Like we need most like least number of coins, right? So
Hmm, that only I don't think so. Like if there is something else minimum than this. Hmm. Basically, for timing, although I'm not able to think of any other example, but if by
ma'am,
chance,
how about 4, 6, 5?
no, we are now given with just these coins which are there, coin values. These are the coin values, and this is I'm telling the number.
Ah, yes, ma'am. I told another example. Like if you take 5, 6, 9, and the maximum is 11,
Then in this way, it is only 5
then
and
you'll
6
get
are there.
5 and 6.
That is like even okay. You're telling
Sorry, not
about
9, 4, ma'am. Not 9, 4. So you'll get 5 plus 4, 9, which is close to 11, but you can even get a better number by 5 or 6. Or if you do 5 plus 5, you'll get a 10. Like there are many possible ways of getting close to 11.
okay. Hmm, fine.
Ma'am, and if there is a situation where uh, two I mean, it is very close. Like one value is 10 and one value is 11, and the actual value to be taken is 11. And but when you take 10, it is only one coin, and when you take 11, it is two coins. So, which one would be the preference? Is it the minimum number of coins or the one which is, nearer to the target?
Here then it will be like the one which is exactly the target. Because if you see the question, it's like return the fewest number of coins that you need to make up that amount. And it's about making up that amount. So even if, like the example which you are saying, if we take that example itself, like you were saying about 10 and one was
One of the value is 10, and then 5 and 6 maybe.
5 and
So 5 plus 6 will be 11, and the target is 11. But there is a 10 which is closer to 11, but it's only one coin. So
anyhow it will number of coins now it will return. Yeah, it will be whatever exact value which is there that it will take. It's like we want to achieve that value, but with the minimum number of coins. But with 10, it's like it is nearer to that, but not able to achieve that. So that's why. So that will be the thing. Now with this much, anyhow, whatever questions you were also having, you told, means you cleared. So now the thing is like how recursive code will be like. Again, the way we were doing that 0 1 knapsack, similar to that, it will be there. Only thing will be there that when we are choosing a number, we are not going ahead with the next number until our present number is something which is having a weight which is now greater than the target. So that is the only thing which will get changed in the recursive code for the same. Else everything will remain same as it is what we were doing in the 0 1 knapsack also. So like would you be able to code it? Like shall I give you 10 minutes for the same? Fine.
ma'am, accordingly, will the time complexity also increase because there are more possible states?
See, in recursion, anyhow, it will remain exponential fine. But in the memoized part, actually, it will be same only what it was earlier. Because, see, index, anyhow, fine, whatever it is. But that target which is there, target, anyhow, to achieve that target, yeah, there are like other possibilities, fine. But all those we are already storing into the same. So that's why it will like remain as it is. Like whatever is was there in 0 1, it will be same here also. Fine, it's 11:25 for 10 minutes. That's 11:35. Fine, I'll ask you at 11:35 then. So here coins as it is, I've taken the amount and starting from zero, from the starting coin itself. Then first time checking if the amount itself is zero, I need to return zero, because anyhow there is a condition that if it is zero, then we need to return zero rather than -1. Then apart from that, if it is equals to coin dot size or less than the amount, that is amount become negative basically, then returning infinity just to check, so that if answer is greater than equals to infinity, so that I can return -1. That is invalid answer is there, else I will return answer. Then when I'm taking, I'm having the 1 plus whatever is there function, so there I am passing, because I'm taking it and I can take it multiple times. That's why then subtracting from that and passing that coins as it is, then I plus 1 when I'm not taking, so that I'm skipping this and going ahead. Then at the end I'm returning minimum out of both of them which is there. Take and not take and not take. What different you were doing there?
I'm checking now. One second.
And even for the take part also, here also we don't require the condition because we already have this check. So that's why that condition is also not required. That is less than that thing.
Oh, ma'am, you have taken minimum of the take and not take. I've taken maximum. Why did I take maximum?
Oh, you were
Ma'am,
looking at part.
from previous question, I got confused. You're supposed to take minimum of the coins, right?
Yep. Return the fewest number of coins. Yep. Fine. And then that should work. Okay, then memoizing part, it will be then same, that index and target which is getting changed. So accordingly, we need to memorize. Same thing here, and whatever minimum we are taking, we need to assign it. And same as it is what the whole question was. But for the bottom of DP part, here, as last time I told that in the 01 knapsack it was backward loop, but here it is forward loop. So here, whatever coin we are choosing, from that we will be starting and going till the maximum amount. So that the benefit of this is so that we are able to calculate whatever was in the future also being stored because of this scenario. We can get that added up in the present one also. So because of this, we will be able to get like this same coin if we can use multiple times in future if we have already used, which was giving us some good answer for that particular weight. So that will help us this present weight, and we can use the same coin. So out of them, whatever minimum will be there, that we will be storing here. And then same scenario here also, we are basically whatever is there, the way there also, whatever negative scenarios were there we were having infinity, but here we are initializing with infinity but starting from the zero. So it's like, because we are taking minimum part, so like if our present itself is having much lower answer, or it is having infinity, or if this one is having much lower answer or infinity, out of them whatever is the one which gives us the minimum answer, so that will get stored into the same. So that's why we are initializing with infinity rather than initializing with any other number or something, because what we want is we want the minimum. So that's why we are initializing with infinity rather than initializing with -1, the way we were in the maximum scenarios which was there. And now comes the part, space complexity, time complexity, all those things. So here in the recursion, it is anyhow exponential. For this, it is n cross amount, because we know that we are taking this n and this is the amount part, and accordingly we are having all the branches and all, and same for the space. In this, we are having time complexity on the basis of the coins, number of coins, on the basis of the amount, till what amount we need to go. So n cross amount, that is for sure. But what we are storing is, we are just storing the amount. That is, our state is like, okay, here I've written minimum coins needed to form amount A. So our state is like that at a particular amount, how many number of coins we are forming, and that should be also minimum, so that we are storing at a particular state, and that is how our state is like. And our transition is that at this particular state and some other state, that is a state where amount minus our present coin was being stored, means that that much amount was being stored, plus when we are choosing this present state. So that is that other state. So after checking that both the state, whatever is minimum, that we will be storing in this particular state, and that is how our transition is for this particular bottom up solution. So is this fine?